obviously we don't chemically make salt, because why wouldn't we do that? Like, why wouldn't companies do that? Because there's so much salt around the world, like, it'd be a waste of money to make it. But it's kind of a cool process because it does produce or release a lot of energy in the process. It's kind of like the gummy bear where it produces a lot of light, smoke, and stuff like that. So I can chemically make salt. We can also cause salt to break apart. If this reaction is exothermic, if I flip it around, then what type of reaction would it be?
Endo.
Yeah, so then it's going to reverse and now be an endothermic reaction. So if a reaction is reversible, if I go the other way, then now the energy is going in. The only way to split salt is we have to send electricity through it, and then it will cause it to split. Otherwise, without that energy, no split occurs. All right, so that energy has to be absorbed or taken in. Okay, so with this idea of equilibrium, it's all about this idea of a rate, okay? That when I have a system that has achieved equilibrium, the forward and the reverse reaction are happening at the same rate. What's rate again?
Speed of the reaction.
Yeah, it's just the speed of the reaction, right? So the rate of the forward is equal to the rate of the reverse. The way we represent equilibrium is we use this double-sided arrow, okay? This right here is the most chemically, this is the most scientific way to show equilibrium, is you actually do two half arrows pointing in opposite directions. So that's what you'll often see like in a problem. I'm going to be honest here, if you want to write it like this, I'm okay with that. Because I know that also represents that it's going both ways. Okay? So what it's doing is there's this competition going on in the reaction where things are changing into reactants, but then reactants are changing back to products. It's just going back and forth, never actually stopping. So for this particular reaction, right, the forward reaction is that this is breaking apart into two things. Okay? This means that in the beginning, the concentration of our reactants is going to go down. In our little video, right, I talked about having a bunch of normal people, and if you guys were molecules, when you run into each other, Haley's arm gets attached to Brianna's face, right? So in the beginning, we start with a bunch of normal people, but as you guys start bumping into each other, some of you lose your arms and the other ones get it. Actually though, right, we'll have less normal looking people in here because you'll have collided with each other, right? And we'll have more of the not so normal looking people because the product is increasing. So on a graph, it would look something like this, is we would see that the concentration of the reactants is decreasing because they're changing into products. And on the other side, the products are increasing. The point at which equilibrium is achieved is the point at which it looks like nothing is changing, okay? So the interesting thing about a system that achieves equilibrium, it never stops. There is no finish, but it looks as if it does, right? To an outside view, an equilibrium system actually looks quite boring. I'm going to show you a demo next time, and it's not boring, but in the beginning it will be, because we won't see anything changing, but they still are, but it's happening at the same rate, so we can't tell the difference. By looking at a graph, the way to know that equilibrium has been achieved is we're looking for the time at which it levels out. So this right here represents when we have reached equilibrium. Okay, so this is the time of equilibrium, is when the concentrations level out. Okay, one key thing, a very common misconception about the word equilibrium is equilibrium does not mean equal concentrations, right? Are my lines at the same spot on that graph? Right? The products, there's more of them then there are reactants. Equilibrium doesn't mean equal amounts, it means equal rates. Okay? So for example, we could consider to an extent my classroom as a system of equilibrium. Okay? So like, there's approximately 35 of you in here right now. Okay? There's about 2,000 people who aren't in my class right now. If my classroom was a system of equilibrium, what that would mean is every time one of you leaves, somebody else comes in. So the amounts are never changing. Are they equal amounts? No. Definitely not, right? It's a 35 to 2,000 ratio. There is a chance you could have an equilibrium that is 50-50, but it's extremely rare. Most of the time you're going to have one that's a little bit more than the others. Okay, so on your own, do a little self-test. Try this question for me. Okay, so question 1 and 2, this is the top of the back page. So for the uncatalyzed reaction, you're going to have to look up here because it's not color-coded on your paper. So you're looking at the black graph, or the black lines for number 1. Okay, tell me when that has reached equilibrium. Then look at the red lines and tell me when those have reached equilibrium. At what time is equilibrium achieved? Okay, by raising hand, anyone have an idea for question number 1? Mitchell, what do you think?
6.
Yeah, so Mitchell says about 6. Why would you say that?
Because that's when the bottom graph starts to,
Good, so that's what you're looking for, right? Equilibrium is achieved when the graphs level out, right? And we see that the black one, it's still curving, it's still curving. So I would say if you guessed anywhere between 6 to 8, I'd give it to you, right? Because it's kind of hard to tell exactly where it levels, but that's when both of the black lines flatten out. Good, Mitchell, have a smiley face for that. Somebody else want to tell us what they think for number 2, for our catalyzed one? Jason?
I put 4.
Good. Yeah, I'd say somewhere between like 2 and 4 for the red graphs, right? Once again, we're just looking for where it flattens out and then stays flat the rest of the time. Good. Have a smiley face for that, Jason. Questions on finding equilibrium from a graph. Common misconception is it's not where they crisscross. We're going to look at some graphs here in a second that don't crisscross at all, right? But we're looking for when they plateau. Okay, so notice that the catalyst reaction, right? We know catalysts make it go faster, and we see that, right? It only took about 3 hours for it to get done. But in the end, the concentrations were still the same. It didn't change where the equilibrium hit. Okay? So catalyst can make it go faster, but it won't change that ratio. Okay, so this idea of the ratio is, it's dependent upon a reaction, right? For example, once again, if we're calling my classroom of the reaction, right? You guys are the reactants. Out there are the products. My ratio is about 35 to 2,000, right? Another teacher's ratio could be different, right? If I go to like our track class, well then the ratio is like 120 to however many students are out of it, right? So the ratio can vary depending on the nature of the reaction, but it's always the same for that reaction, okay? So a word that we're going to use a lot here is this idea of favored, okay? When I say that a reaction is product favored, what that means is that there's more product than there are reactants, right? Even though there may be some reactants in there, there's more products. Or if it's reactant favored, then there's more reactants, okay? Please answer this question for me on your own. On your paper, based off this graph, is this reaction product favored or reactant favored? Okay, so last thing, before we play our little equilibrium game to help us understand this better, okay, is the thing that is equal about equilibrium is the rates. Okay, it's not the amounts, it's the rate. The rate of the forward is equal to the rate of the reverse. Or another way you can think about it is they're happening at the same speed. Another system of equilibrium that you can relate to is a treadmill. right? A treadmill is a system of equilibrium because in order to stay on it, you have to move forward at the same rate that it's pushing backwards, right? If you move faster, you'll run into the wall. If you run slower, then you'll fly off the back, right? So on a treadmill, right, if I'm at equilibrium, so I'm staying in the same place, does that mean I'm doing nothing?
No, it's not moving.
Definitely not, right? That's the thing is, it's going to look like nothing is happening to an outside view, right? If I wore my GPS watch on a treadmill, it would tell me I went nowhere. But a lot of work had to be put in order to maintain it, right? So that idea is called dynamic. That's why it's a dynamic equilibrium, is because it's always changing even though we don't see the change. This idea, okay, they're going to find that same ratio in the end. Okay, key thing is it's a ratio. It's not the amounts are equal, but the ratio will be maintained no matter what when it's at equilibrium. Same equilibrium ratio. So what we'll talk more about next time is this idea of if I have a system at equilibrium and I apply a stress to it, the system is going to work to find the new equilibrium. Simple example, but once again, if you're on your treadmill and you want to stay on your treadmill and the speed gets faster, in response, you're going to have to start working harder as well to stay on it. A chemical reaction will do the same thing. If I cause changes to it, it will shift it and it will find its way back to equilibrium. So that's kind of will be the focus of next time, is those different stresses and how it shifts.